Now we're going to turn our attention to some of the nitty-gritty details of how to write a correct C program. And we're going to look at a very simple program. I'm going to show it in its execution window, but first I want to discuss what we're going to look at. So this program is going to print the sum of two floating point numbers, and it's going to use simple I/O. It's going to use a scanf to read in the values and then printf to show the results. Now, the elements of a C program are made up of characters, so it's just like an essay in English, except an essay in English could be understood even if you have misspellings and punctuation errors. In case of a C program, spellings, punctuation errors, mistakes of that kind get caught by the compiler, and the compiler won't let you run the program, even though you think you understood and it should have understood these simple mistakes. Now, hopefully, a good C compiler will give you informed messages that make it clear what it thinks is wrong. So, first off, a program in C assembles a bunch of characters into what we call tokens. And let's look at a little of what a token is. So, these tokens or lexical elements might be comments, for example. A comment is something that starts with /*, and then can be any set of characters. So those set of characters get ignored until you see an asterisk slash. What if you forget the second part or write this incorrectly? Then this is going to go on forever, and you'll get some error message, hopefully, that'll say you didn't complete your comment. A second thing you'd see that we've seen already in C programs are preprocessor directives. And the biggie is sharp include. So a preprocessor directive starts by putting a sharp. Typically, by convention, the sharp should be at the beginning of a line. And then we have a number of possible special words. And include is one that says to the compiler, the following library should be included. And we, of course, have already made use of standard I/O. But there are other important libraries like the math library, like the character processing library, like the library that includes timing operations, time.h, and there are multiple very important standard libraries that you're going to have to get familiar with. Another big part of having a program be correct are things like identifiers, and these are possibly multi-letter, but they can be as much as single-letter tokens. So A and B can be an identifier, and we'll see that in the next program. And main is a typical identifier because it indicates it's special in the sense that it indicates where the program is going to start executing. We also have tokens that are operators, so plus is a token for binary operator, or in context it could be a unary plus. Ampersand is an operator meaning address of, but again you gotta have context, so sometimes you could see two ands, and two ands are the operator for logical and. And then there's punctuation, also highly important. So we've already seen punctuators like the open brace and the closed brace and the semicolon. And each has an important use in the language, and you must get them to correct, or else you'll make fundamental syntax errors. So a program must end up being syntactically correct. So we write a program, we get our ideas down, and then we have the compiler check that it's syntactically correct. So here's a possible syntax error message. We'll have int main paren, and then rather than a curly bracket, we might mistype and have an open parenthesis, and that would be wrong. So the compiler will issue some message. Hopefully it'll be informed. It almost always points you at where it sees the beginning of the error, and then hopefully it gives you an English language message that is helpful. But you have to make sure you understand where the error occurs and how to correct it. Then harder than that is to get the program to work right, semantically correct. It works. And here is where we possibly repeatedly run, modify, and retest the program until we get it right. Okay, the next segment will go on to the actual code for the program in which we've seen these tokens parsed by the compiler compiling, and then executing. So in this segment, we're going to look at tokens of the language that are called keywords. Also, in other programming languages, they were sometimes referred to as reserved words. And I'm going to use my browser to look at. You can get many tables for this, but it makes it a little easier. So this is the standard ANSI C recognizes the following keywords. And there are some additional ones, but I'm going to start by grouping them. And it means that they can't be used for other purposes. So you can't use them as ordinary identifiers. Now keep in mind, certain things that look like keywords aren't keywords. So typically on an exam, a simple mistake is to think that main, M-A-I-N, is a keyword because you're seeing it all the time as an identifier that by default introduces the execution of the main C program. But main is just a keyword. Another thing that might be thought of as a keyword is actually a special word for the preprocessor, which is something like include. And words that get introduced by the sharp sign, like sharp include or sharp define, while they have special purpose in the language, in the C compiler system, they are not these reserved words or keywords. Now, a number of the keywords, like double, float, int, long, char, those get used to declare data types. Those are used for the built-in, or what we call the native data types of this language. Another one of those is enum. So they're one category. So let's look at char. We'll get a further definition by clicking on it. Int and char, basic data types for integer and character. Variables of type int are one machine word in length, and that's typically on most machines 4 bytes now. They can also be modified by signed, unsigned, short, and long, but that's for a later time. So character types are very important. They are the basic types that you're going to work with in the language. The int type, which is one of our most basic here, is a range of int typically represented between roughly 2 billion, minus 2 billion, and plus 2 billion. In the signed type, and in the unsigned type, it's 0 to 4,294,967,295. Break, continue, go to, for, if, These are all keywords else that affect the flow of control of the language. Later, we're going to go and show you what an if-else statement is. We're going to avoid goto, so consider goto obsolete. Goto is a way of jumping anywhere in the program code, and that's considered a no-no. And in fact, some languages now no longer allow goto. Return, we've seen in a lot of our simple programs, and that just means finish the execution of the current function, and if it's return of an expression, it returns the expression value to that function from where it was called. Later, we're going to see fancy things like typedef. They're a way of giving new names to types or frequently compound types. There's some specialized types like union and struct. Struct will be heavily used, but in part B of this course. And union, not so much. Generally, union can be avoided. Now, among these keywords, auto is obsolete again. Auto is just rarely used, unneeded. It's what's called a storage classification. Among the storage classifications, you have auto and you have register. Again, register is unneeded. Register says, place whatever this is into a high-speed storage. Well, it turns out the compiler can do a better job than you can do. And indeed, modern C systems are running on things that don't need this kind of programmer-directed optimization. So you're not going to see auto, you're not going to see register, you are going to see static, but it has a very special set of uses. Those are storage classifiers. So get used to this keyword list. I think there's about 30 in this keyword list. Most of them are critical concepts, but the nice thing about a language like C, it has a relatively small number of these. In current C++, the number of keywords exceeds, I believe, I'm not exactly sure. Why don't we look it up? So I'm going to use my compiler, ANSI C++ keyword table. And you can see this is a very much bigger set, includes as a subset things that we saw in the other case. And indeed, C will let you migrate to C++, but we're not starting with C++ because look at this table. It's what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's about 96 if I'm counting right, and indeed there are some other things that are special context. So roughly speaking, C++, modern C++ has 3 times the keywords, and you can imagine that in many ways it's 3 times more complicated, though of course you don't have to use the full language. Okay, enough said about keywords. In this lecture, I'm going to talk more about identifiers. When you write code, you will see in the code tokens that we call identifiers. So we've already written code where we see int main paren paren. The int is not an identifier, it's a keyword. Main is an identifier. It's the name of the function in which execution starts, and the parentheses are not part of the identifier. Parentheses get used for a function call. Now, one of the key parts in writing good documentation in any programming language is proper choice of an identifier, and we have to know the rules for how to choose an identifier. And here's a shorthand for the rules. I'm not going to do much of this, but and I'm going to explain it. This is what is called a syntax equation. Identifier is sitting on the left side. An identifier in C is made up of a letter or underscore character in which you have at least one. Letter or underscore. This straight line means or. Letter or underscore. And when I subscript by one, it means I have to have at least one of these. And then following it, I have a letter or underscore or digit, and I can have that 0 or more times. The plus sign means as many times as I want. So identifiers can be arbitrarily long. Generally speaking, you're not going to see identifiers that are more than 10 or 12 characters. That would be as big an identifier as you're likely to see. In C, what conforms to this? Well, the simple one-letter identifier K, frequently used for integers that are auxiliary integers in writing your code. Underbar printf, that could be an identifier, and in fact, that's probably the identifier that the systems programmers used when they designed the printf function. Here is a common thing you see. 2 words. When you have the 2 words, you have 2 underbar words. The underbar, or the underscore character, I should say, the underscore character is used to separate distinct words. So when you want an identifier, but in English you want to have more than one word in your description, one convention is to use underscore. Another convention is to tie the 2 words together with a capital. So to capitalize W, the beginning of the second word, and that would also be another standard convention. What you shouldn't be doing is mixing them. And then here's another standard identifier, my underscore DNA 23. And remember, once we're past the first digit, we can use digits as well. What won't work as an identifier? The sharp character. So sharp me is not an identifier. Sharp is not allowed anywhere, so or me sharp would not be an identifier. Here, rather than underscore, I'm using minus, and that would be the expression unary minus x. X could be an identifier, but minus x is an expression. And 23 my DNA is not an identifier because the first character of that sequence is a digit. So that's not allowed. So digits are allowed anywhere but in the first character. Underscores and alphabet are allowed anywhere, including the first characters. Now, good choice of identifiers in your program help you document the program and make the program readable. Main, printf, square root, sqrt, those are actually things you'll see very commonly. Printf and square root come from standard library. And Superman, if somehow you're writing some code to exhibit something to do with the character Superman, maybe you'd call that, you'd use that as an identifier that gives you a clear image, as does radius. And I as well. You have, it's a convention in the community, in both the programming community and mathematics community. When you want something that's for counting, you can use I, J, and K. Also, you frequently can use N as another understood integer. Those would all be good choices. Of course, you have to use them for the right purpose. Here are some things that might be bad choices. GRX33 underbar PP underbar 25, I underbar am underbar 4 words. Well, GRX33 and this underbar PP stuff, we have no concept of what they might be. So they're not going to be readable. They're not going to provide some kind of documentation. I am 4 words makes sense, but we've mixed 2 conventions. So that sort of would, in a way, take away from the goodness of I am 4 words. Other things we aren't going to necessarily know if they're good or bad. Let me put some up. They're going to have the right context. So data may or may not be good. It may not be adequately descriptive. Maybe you need height data or weight data or something else. Mxyzptlk, I'm not sure I'm pronouncing that right. Maybe that's an okay identifier. Maybe not. Let me exit this. If we look in our browser and we look up DC cartoons, here's Mr. Mxyzptlk. He's a typical foe of Superman. Superman always has to get him to say his name backwards, which again is very hard to pronounce. I'm not sure if it's Kitazimavik, whatever. And again, if you were writing some movie with Superman and Mxyzptlk, it might be an appropriate identifier. X might be an appropriate identifier, especially if it's something like a coordinate in the XY plane. Then it would make perfect sense. Again, we've said if we use J for integers, fine. Q may be good or bad. Maybe it's obscure. Maybe we're doing something like logic programming. And in the logic community, P and Q are typically chosen to mean Boolean variables. So if we were doing logical evaluation, P and Q might be quite appropriate. Again, that's contextual. So they might be either good or bad. Let me finish by looking at a very simple program that hopefully follows these constructs. Here's a piece of code. It's for computing the area of a circle. Notice we have main, that's an identifier. The capitalized pi would be an identifier in C, but that's a preprocessor command, and in the syntax, this must be an identifier, and then it's associated with this constant value, and it's typical. Another convention is when you have such a constant, you capitalize it. Again, there are community conventions that should be understood to make your program readable. You want an experienced C programmer to say, aha, I can read that and understand it clearly. So here we have two identifiers, area and radius, and we understand their meaning. That's how we're going to use them in the program. Double, of course, is a keyword. Then we have printf, scanf. They're both standard identifiers found in the I/O library and standard.io.h. There's area equals pi times radius squared, and so on. So this program abides by my conventions, has good choice of identifiers. In this segment, we're going to talk about expression evaluation. C is a language rich with operators, and it's very important to know how the operators allow combination, in what order they're applied. I'm going to show you some very simple cases so you can get the central idea, and the central idea is going to be know how the operator works, know its precedence, and know its associativity. So we're going to start with three very simple variables. As we declare them in C, we would say int a is initialized to 1, equals in an declaration is the initializer symbol. Int b is initialized to 2, and int c is left uninitialized. Normally, most systems would make that 0. So we have three variables to work with in our code. Here's a very simple expression using those. C is this equals means assigned. So in this case, we are seeing an assignment statement. Read that as C is assigned the expression a plus b, semicolon is a end of the operation. So it's signaling a sequence, what's called a sequence point in the computation. Everything that happens on that line, and then you're finished, and then you go on to the next line. Now, as we know, A was initialized to 1, B was initialized to 2, so we would expect C to become 3. So this is a assignment expression. Inside it is a binary plus operator, and that says C is assigned a value of, and here we use parentheses, a plus b. And parentheses are critical in the C language when you're evaluating expressions, because they always override any other part of the expression's precedence. So they clearly show, if you're confused otherwise, or it's a very complicated expression, that this is how you want the order of evaluation to occur. So as we just said, C becomes 3. That should be straightforward. Let's go on. Precedence. Well, we have something like 16 levels of precedence in C operators. Things that are very low precedence, for example, tend to happen later or last. So assignment itself as an operator has very low precedence. However, certain operations, like unary operations, like the operation negation, which is found when you're doing some logical expressions and where you use the exclamation point, is a very high precedence operator, as is something like auto-increment or auto-decrement, which are operators that use the symbol plus plus and minus minus. And then somewhere in the middle are arithmetic operators. And in the arithmetic operators, you have multiply, for example, which in this case is featured with this star. And that has a higher precedence than simpler arithmetic operations, plus and binary minus. By the way, note that you can also have unary minus and unary plus. And the only reason you would know the difference is context or parenthesization. And a unary operator like these are higher than the corresponding binary plus and minus. So binary plus and minus take two arguments. Unary takes one argument. And then times, and indeed things like multiply and divide are higher precedence again. And there's also on that level the remainder operator percent, which again, or sometimes called the modulo operator or remainder operator, which is also a higher precedence, equivalent to a multiply or a divide than the addition operator or subtraction operator. Why is that important? Because if these get mixed up in an expression, you have to know which goes first. The other thing you need to know about is associativity. How do the operators associate? So when you have an operator a plus b plus c, this has got two operators. Which goes first? Do you apply b plus c first and then do a? Or do you do a plus b first and then c? And it turns out that these operators occur left to right. And the overwhelming number of operators are left to right. And we show the equivalent parenthesization here. So we would get a plus b, parentheses, plus c, parentheses, if we wanted to fully parenthesize this expression to make it clear what the implicit order of evaluation based on associativity were. Now, looking at this other expression, a assigned b assigned c assigned 3, we get right to left. That means the c assigned 3 occurs first, then the b is assigned that expression value, then the a is assigned. And what you'd all end up with is everything would end up being 3. All right? Try to absorb that. Make sure you can write code of this kind and know how to evaluate it. And we're going to go on to more complex expressions with different operators involved. Okay, we're going to go on to more complicated expression evaluation. We're going to look at some more involved cases. One of the things that gives a lot of people trouble at first is to remember that tokens like the slash token have different meanings in different contexts. So besides the fact that a slash token can be used to be part of a comment, a single slash is generally a divide in an expression, but that divide could be either the integer divide operator or the floating point divide operator, and that gets determined contextually. Similarly, people have trouble with the remainder or modulo operator, the modulus operator. Somehow they don't use that as much in daily practice, so it's hard for them to remember how that works. Then there are operators that are unique to the C language, and they include auto-increment and auto-decrement, and they are plus plus and minus minus. And then there are operators that are based on assignment, so they are ordinary assignment, but also an operator like plus assign. So you might see plus equals or minus equals. But when you see equals equals, that itself is a logical operator. So context means a lot. And I shouldn't say these things are unique, because while C pioneered much of this stuff, they do get used in typically languages derived from C, or with some inspiration for C, so you'll see such operators in Java and C++ as well. Now, if stuff gets too confusing in expressions, then to unconfuse yourself and people reading the code and maintaining the code, use parentheses. And keep in mind that parentheses override the built-in precedence and associativity of the operators. So A times B, which is high precedence, then plus, if you had A times B plus C without parentheses, it would mean that first thing. It would mean first do A times B because of its higher precedence, then add in C. But if you wanted A times B parenthesize C, then you'd have to use parenthesize, because that would override the precedence and associativity of those, the built-in ones for those operators. There are also gotchas that you have to keep in mind, and a typical one is the use of divide when it's an integer divide. You don't have this problem with multiply, but 3 divides 7 is going to be 0, whereas 7 divides 3 is going to be 2. And in those cases, there would be a remainder, and the remainder just gets thrown away. But 5 divide 2.0, because 2.0 is a floating point constant, is indeed 2.5, which itself is a floating expression. Finally, the modulo operator, as I say, you have to familiarize yourself with it if you haven't used the idea of modulus for a while. That's just what a remainder is in an integer divide. So 3 modulo 7, the remainder would be 3, or 7 modulo 3, the remainder would be 1. Here's the use of pre and post increment. These are specialized but very useful because they abbreviate what would take some more writing. So the pre-increment, namely plus plus b, what it means is b is assigned b plus 1. So b plus 1, the increment, gets done first. Then the assignment a is assigned the resulting value of b after the increment. In the post case, which has higher precedence, by the way, a assigned b plus plus, it's the equivalent as a is first assigned b. So if b was 5, a would be 5, but then b would become 6. All right, so I hope you'll experiment, and I'm going to show you an experiment right now. I'm going to switch over to my runtime window. So here's some code I wrote earlier to experiment, and this is code that you should try to either copy or write your own code of this kind and just try to check your understanding of evaluation, make sure what gets done on the machine is what you expected. So in the first case, we have equals sign, meaning initialized. So a is initialized to 5, d is initialized to 0. Then we have an expression where c is assigned a minus b. Well, a is 5 and b is 7, so we'd expect 5 minus 7 to be minus 2. So if we use that print statement, we should see a is equal to 5, B is equal to 7, C is equal to -2, and D is equal to 0. Now, in this part of the code, we're seeing how integer divide would happen. So 5 integer divide 7, that's going to be 0. D will be equal to 7 divide 5, so that will be 1. If this had been all in floating point environment, if everything had been set up as floating point, then instead you'd have the equivalent of 5/7 in floating point, or 7/5 or 1.4 for D. But that won't happen. You're going to get 0 and 1. Also, further on here, I won't look at the module, I'll let you work that out, but here's an interesting one. Here we see the difference between unary minus and binary minus. And unary minus has higher precedence, so that occurs first. So 5 becomes -5, and then we have a binary minus where we subtract 7, positive value 7, and the result should be -12. Here we're seeing the difference between prefix autoincrement. So A will move from 5 to 6, but this is postfix autoincrement, so B remains 7. So 7 plus 6, C will become 13. But then when the whole thing is executed after assignment, then B will become 8. And here we see the plus assignment operator. So this means whatever D's value was, where in the earlier case D would be -12, we would add in 5, so we'd end up with a -7. So again, try to understand all this, and then here's the actual running of the program results in these values. And I will write a quiz for you and most likely put something of this kind on the class final. In this segment, we'll talk about the structure of the program that includes declarations and an especially important operator, assignment, and how it relates to expressions as well. And all this is wrapped up with types. So we're going to talk in detail in the next few segments about the type logic of the C programming language. Now, types. Some of the types we've seen already are int and double. There will be other types. There will be other simple types like char, float, unsigned, and then there'll be more complicated types later on that involve structs. For the moment, we'll concentrate on these two distinct types. Int, which is in effect an integer type, supposed to represent precisely the whole numbers, and double, which is a floating point type, which is supposed to represent scientific numbers with a very large range. Now, a declaration is a simple declaration is going to look like a type followed by an identifier with a semicolon. So here we see a simple example on this side. Then a more complex example is a type identifier followed by the equal sign, the equal character, and an initializer. this is not assignment, this is initialization. It occurs in the declarations. Declarations, by the way, occur at the head of a body of code or at the head of the program. And here we have, again, a very simple example. Int, the variable a assigned to. So there we mean that we're going to, in that piece of code, treat a as something that can get different values as long as they're integer, as long as they fit within the type int, and we'll explain more about what it means to fit in the type int, and 2. Finally, we can have a more complicated type declaration in which we have a list. So here's one of those. Int a assigned or initialized 3, comma. So it's a comma separated list. It can be arbitrarily long, and this has 2 variables, one initialized to 3 and one initialized to 5. Okay, let's restart. Here we have a piece of code that I already typed in. It's supposed to show you an example of the use of elementary declarations and assignments. In this piece of code, again, at the head of what's called the block starts with that open brace. We have a declaration list with initializers. So A is of the type int, B is of the type int, C is of the type int. And if we think about what's stored in their memory location, A is 5, B is 7, C is 6. And then we're going to do a simple averaging, and we're going to use a variable average, and that average is going to be initialized to 0.0, though that may be unnecessary, because it's just good practice to initialize variables, because sometimes when you forget to do that, it can lead to errors if you allow the system to do the initialization for you. Here's a printf that'll show us that we assigned what we've assigned, and then we're going to do an average. And in this average we see a plus b plus c. Normally that's an integer expression. We divide by 3.0. Why? Because if we divide by 3, this will be purely an integer division, and we may have a rounding error. But we want it to be done in double. We're going to talk more about why this occurs as a double. This expression will occur as a double. So this is overall an assignment expression, but conversion would have been, if there was a 3, we would make this an integer expression and then assign it to a double. In this case, this is a double expression assigned to a double, so there's no conversion. And again, as I say, difficult topic, very tricky. We'll talk a lot more about conversion. And here we just print it. So it's a very naive program. Let me escape. And I compiled it already, and let me run it. And sure enough, A is 5, B is 7, C is 6, and the average is indeed the floating point number 6.0. So let's continue to talk about the C fundamental types. There will be other types later on, like pointer types and struct types and enum types. But for the moment, we're going to concentrate on a fairly simple set of types. Maybe not that simple. And our early computations will do a lot with int and double and char. And intuitively, you can understand that a char might be a special character like A or a capital N, or the character that's the digit 5, which is going to be different than the value 5, or an unprinted character that moves your screen a line, so that's represented by \n. So the characters can represent what's called the ASCII table of characters. It's typically all the lowercase, all the uppercase, punctuation, operator characters, digits, and some special characters like new line. The integers are pretty much what you're used to since grade school. They're numbers like 0 or -3 or +77. And then finally there are doubles. These are more like the scientific notation. And there you get numbers like 1.245 or 3.2 with an E, which designates that something is an exponent. The exponent is a power of 10, so it's 10 to the 5th. So that's going to be 320,000. Then we're going to allow the fundamental types to have further modifiers. The two critical modifiers are going to be unsigned and long. The idea of unsigned is going to apply to strictly the integers, and that's going to mean that you're going to rule out the negative numbers. Long is going to apply to both the integers and to the doubles, and they're going to mean, well, we might have a range, which typically for the integers is plus or minus 2 billion, and we want a longer range. So that will increase the range of those numbers significantly, and we might need it for a bigger calculation over bigger numbers. Finally, the same thing is true for doubles. We're actually going to have 3 kinds of doubles. We're going to have float, double, and long double. And on a typical implementation, these are going to be longer and longer, and therefore capable of storing a bigger and bigger number. Well, it's not like mathematics. It's not like you can imagine a number like pi, in which there's an infinite number of decimal places. So the mathematician's conception of pi is potentially this infinite string. That's not doable. The computer memory is a finite resource. It's organized in terms of bytes. A byte is a unit of memory, which is conventionally 8 bits, and 8 bits can only store so much information. Basically, they can store 2 to the 8th. So here's a number that could be stored. Typically, these things are bits, so 0001010. Remember, computers are binary, and they store bits. They store them somehow electronically, magnetically, unless you're going to work with some kind of fancy quantum computer. But on all our actual digital computers, modern digital computer uses a base 2 designation and bits to represent whatever you need to represent when running a piece of computer code. Well, if you look at this, this is the zeros place. This is 2 to the 4th, 2 to the 3rd, 2 to the 2nd, 2 to the 1st. Excuse me. So 2 to the I have this wrong. This is 2 to the 4th, which would be 16, and 2 to the 2 squared is 4. So we're going to actually get the number 20. Very easy to make a mistake if you're not a computer. On a typical machine, an int is 4 bytes, and an int can be used to represent between roughly 2 billion, minus 2 billion, and plus 2 billion. This is more exact. So actually, this is equal to 2 to the 32nd minus 1. And that shows you 4 bytes can be used to store 32 binary digits. One of the digits is going to be used for the sign, so that leaves 31 digits for everything else, and that's why this can be roughly 2 to the 32nd minus 1. Now, when you write your code, you need to know what is representable. The way you can find that out, you can see what a type will store by using a built-in operator, one of your keywords in C, using size of. And we're going to show that. So one of the funky things about C is certain things can be system dependent. Why is that? Because C attempts to be efficient in relation to the underlying computer. So it's not attempting to have universally the same semantics, because some computers have very big word sizes and some computers have small word sizes. And C wants to run efficiently on a computer that has an int size of 2 bytes, as well as a supercomputer that might have an int size of 2 bytes, as well as a supercomputer which might have a 16-byte int. So you do have to know and realize that you're running on a particular system, and you can even, if you're a very sophisticated programmer, ensure that your system has sizes that are appropriate for your computation. And you can look at that dynamically by using this size of operator. You can see it here. There's a size of print, a size of long int, a size of a char, and here you see you can use a variable. I could have said char, but I can also use the variable. So size of will operate on either a variable name or on an actual type name. Here's float, double, and long double. And let's execute that program for the system. It's a Macintosh system. And there, on my system, an int is 4 bytes, a long int is 8 bytes, a char is 1 byte, a float is 4 bytes, a double is 8 bytes, and a long double is 16 bytes. So you should go and try that on whatever system you're using. So we're going to discuss the fundamental type char. Char is going to let us do a lot of text processing. And char is the constituent in a string. Later we're going to understand how strings are just series of char. Actually, when we learn more about that, we'll see that a string is basically an array of char with a sentinel character at the end, which is basically a 0. So char is a fundamental data type, and a literal or constant char includes things like the lowercase letters. There's they're represented in your code as single quote X single quote, but also you could have a digit like 7, and it would be represented again, unlike it wouldn't be 7, because if 7 was without the quotes, then it would be the literal or constant int. And then, for example, there are also, and we've already used them, non-printing characters, characters that don't show up directly on the screen but do something. And the most common one is \n, which tells you to advance to a new line. Now, you don't have to memorize this, but in most texts or online, you can find the values of the standard 0 to 127, so it's actually a table of 128 characters that can be printed, or the non-printing characters that will do some action on your computer system. And among those characters are, for example, the uppercase. And what's nice about the uppercase, if you remember, capital A is an integer value 65, then they actually appear in the ASCII table adjacent to each other, and capital B is 66 and capital C is 67, and so on until you reach capital C, which is 90. And similarly with the lowercase, though they're in a different place in the table. So lowercase a is 97, and then it sequences all the way to lowercase z, which is 122. This is a bit confusing. Digits, when you use them as char, have a value. So the digit 0 as a character is actually integer value 48, and it is also a sequence from 0 to 9. So you have all the decimal digits available for purposes of using them as char or internally in a string, and they range from the integer value 48 to 57. And then there are others, all the other characters you find on the keyboard, and these are punctuation characters and operator characters and special characters like $, and they're all available in the ASCII table, and they all have a particular integer value, except unless you're a memorization freak, you're going to have to look them up. But of course you can quote them, and then they will indeed also have this internal integer value. And one of the things about this is you can store these in a byte. So you can use 8 bits and store the entire, any of the ASCII values. Now, non-printing characters are very important as well because they promote actions on your computer system. \n, see, you can't have n because that would be printed as n, but \n sort of escapes it. So the idea is \n is a special non-printing character, and indeed when you put it in a printf, integer value is 10, but what it does is advances to the next line on the screen. \a is also a non-printing character, and if its value is 7, and if you were to use it inside a program, it would, on your system, ring a bell or make a sound. So that's the character set you can use. And now let's show a simple program for how that may be used. So I wrote this program to show how it would be used in a very simple way, and just show how the characters, when printed as a %C, see here, %C is in that format string, that's going to print out as a character. Notice the character is declared, the variable C is a character variable, and we're going to assign it, again, quote, single quote, a single quote. And now we're going to print it in two different ways. In the first way, we'll print it as a %d, so it should show up as an integer. In the second print, it should show up as a character. And then we're going to do the following to show you that these values, the ABCs, are going to be sequential. So we have 3 characters to print, and they're going to be C, C+1, and C+2. So those are integer expressions, but they're interpreted as a character. So in effect, the ASCII table gets used to show what gets printed. And here, if you run this on your local system, you should hear something. You should hear 3 distinct noises or bells. And here you have this \A, which I talked about as a non-printing character. Of course, there's a non-printing character here too, and that's in the string, and that's interpreted by printf. So printf knows how to interpret that. And if I had put that over here, if I had made that a character to be printed using the %c, then what I see is nothing but an advance of the screen. So let's run this. I already compiled it. And you see its output. The character C has an ASCII value 97. As I said in the beginning of the lecture, that's the character A. So when I print it as an integer, it printed as 97. I print it as a character, prints as an A. The 3 consecutive characters that got printed are ABC, just as we expect. The 3 bell rings, nothing got printed, but I heard them locally. I don't know if the microphone picked them up, but there was a bing, bing, bing. That were, in fact, the printing of those 3, quote, non-printing characters.